So now we are going to start talking about the first form of energy, which is the kinetic energy. And just to give you a heads up before we go into the details, these forms of energy most probably are gonna be known to you, so you know them. You know, even the equations that we use to calculate them might be familiar equations for you. So what we're going to do is to go through the definitions of the forms of energy and the equations that we use to calculate them, some terminology that we will agree on, the symbols and all these things, so that when we talk about the equations later, we are all on the same page. So when we talk about the first form of energy, it's the kinetic energy, and the kinetic energy is the energy due to the motion of the system as a whole relative to some reference point or reference frame. And this reference is usually the Earth's surface, and this is how we calculate the kinetic energy. You say that it's the calculated based on the velocity relative to the Earth's surface. So there is other type of kinetic energy, which is the rotational energy. If the system is rotating around a specific axis. In our case here, or in this course, we are interested in the what we call the translational motion, which is the motion in direction, not a rotational motion. So it's the one that we are interested in, and we calculate it using the very famous equation, the half mv square, or in this textbook we use the symbol u for the velocity. The ek is the kinetic energy. So and in some other references it's written as k dot e dot, and potential energy is p dot e, but here it's e sub k. So this is the way we define the kinetic energy. And this is the kinetic energy if this is a specific mass, but if we have a flow rate, so we have m dot, in this case we'll have e dot sub k. So this is how we calculate the kinetic energy, and of course the units of kinetic energy are units of energy, so it's going to be in joule if it's just mass. If it's mass flow rate, then it has the units of joule per second, which is watt. So it's going to be E dot. Will have the units of watt, and E will have units of joule. So anyway, so this is how we calculate it. For the potential energy, it's the energy due to the position of the system in a potential field. The very famous is the potential field is the gravitational field. This is the energy due to the elevation from the surface of the Earth. Sometimes it can be calculated based on the electromagnetic field. Again, it's not part of our interest. We are only interested in the gravitational field. So in this case, it's calculated from the symbol, from the equation mgz, or z sometimes is written as h, depending on the textbook or the reference that you're using. Again, EP is the potential energy. If we have flowing material, then we'll have m dot instead of m, and in this case it is m dot gz, and again it will be in the units of joules per second or watt. Of course, g is the acceleration due to gravity, z is the height, m is the mass. Again, the units of this would be in watt, in joules. This will have the units of joule per second, which is watt. The kinetic energy and potential energy, again, we said before that the energy can transform from a form to another, and this is something that we can see in this very famous example when you have a waterfall. The liquid at the top of the waterfall has very high potential energy, and the velocity is not very high, so it has low kinetic energy. And once the fluid starts to go from up to down, as it goes down, its potential energy decreases and the kinetic energy increases. So the potential energy is transferred into kinetic energy. And this is a very clear example of the energy transfer from a form to another. So this is these are the first two types of energy. The third form of energy is the internal energy, and the internal energy is the energy that is possessed by the system, and it's defined that it's the energy, any other energy other than the potential and kinetic energy. So it's the energy stored in the system. This energy can be in the form of motion of molecules relative to each other. So this is in a micro scale motion of molecules. It can be the rotational or vibrational motion and the interactions between molecules. It can be the interaction between atomic and subatomic constituents of molecules. So these are all sub or atomic or molecular or submolecular forces that happen inside the system itself. So this is something, and this is a very important thing, because we will come back to this later, that this is something that we have no way to calculate it. We cannot calculate how much energy is there between the molecules. There is how much energy due to the collision of molecules. We cannot see this. We cannot observe this. We cannot calculate this. So back to the definition of the systems, we will start with the closed system, because the equations that we are going to use are easier than the open system, and we need the definition of, or the derivation of the closed system equation to use it for the open system. So for the closed system, we said before that the system has its energy that is stored in it, either in the form of kinetic potential or internal energy. And we said for closed system, and if you go back to the previous video, we said the definition of a closed system is the system that has no mass crossing the boundary. So there is no mass going inside the system or mass going outside the system. But we said that a closed system can have energy going in and out of the system. So the closed system can have some energy transferred into or transferred out of the system. So you can add energy to the system from outside or remove energy from the system to outside. This form of energy can be in the form of heat or work. So these are two more forms of energy that we need to deal with or understand, because we will include them in the energy balance equation. So again, just to differentiate between what we said before, the three forms of energy, the kinetic, potential, and internal energies, are the energies stored in the system. These energies can increase, can decrease due to the change of the energy that is due to the energy coming from outside or released from the system to the surrounding. This energy coming from outside or released to the surrounding is either heat or work. So this the heat is the energy due to the temperature difference between the system and surroundings. So if you have something that is hot, it will spontaneously transfer heat to something that has less temperature. The heat is, and this is important, and we will come back to this later, that heat is positive when it's gained by the system. So if the system is gaining heat, then we put a positive sign for this Q. And this is a very confusing thing for some people, because references deal with these signs in different ways. Sometimes references would do the opposite to what we are saying here. So some references say that if heat is gained, it's positive, and if it's lost, it is it's negative, and the other way around. In our reference, or the textbook that we are using, is putting a positive sign when the heat is gained. So if the heat is increasing the energy of the system, this is positive. If it's reducing the energy of the system, it's negative. So we will stick to this signs so that we don't have any confusion, and this is the way we put the signs from now on. The work is the energy that flows due to any driving force other than temperature difference. So it can be due to force, can be due to torque, can be due to voltage. So any other form of energy other than the temperature driven energy is called work, and the same applies here. We say that work is positive if it's transferred to the system. So if the surrounding is putting work on the system, so this is positive work. If the system is putting work on the surrounding, it's negative work. And let's take this example. This is a very nice example, actually. So let's look at this. This is a piston, and this piston is we can consider this as a closed system, because this piston contains the gas inside. There is no flow of gas outside or inside the piston, so the gas is confined in this place. We have a force that is on the system, which is due to this mass. And then we have heat. So this is energy that is transferred to the system in form of heat. So if you look at this, the transformation from this state to this state, we have the energy. The system gains energy because of the heat, so there is heat gained by the system. In this case, we have positive Q because the heat is going inside the system. At the same time, the system is the heat is leading to the expansion of the fluid, and this expansion is leading to the pushing the piston up. So as the piston goes up, then this is work that is done by the system on the surroundings. So this is a negative work. So this is positive heat, this is negative work because the system is doing the work on the surrounding. Here we have the mass, it's removed from the piston, and in this case, yeah, we can assume that or we can tell that this mass is doing some work on the system, so this work is removed. So this is yeah, we don't have any motion on the boundaries of the system, so this is not considered the work. Now, if you apply work on the system, maybe you're putting some heavy object, you're pushing it by hand or by any ways, this is work that is done on the system, and at the same time there is cooling, so you're absorbing heat from the system. So the heat now is negative because it's absorbed, and the work is positive because we are doing work on the system. So going from here to here, we have positive work, we have negative heat. So this is a nice demonstration just to understand the meaning of the negative and positive heat and work. Again, we will go to this later in more details. So we will stop here, and next video we will start putting everything together. We will start with the basic principle of conservation of energy, and we will see how this principle can lead to derivation of the energy balance equation for closed system. So we'll see you next time, inshallah. Goodbye.